So I recently graduated from Ohio State, and this talk highlights my thesis work on anisotropic hydro. So one of the main objectives in heavy ion collisions is to accurately model the complex dynamics of a heavy ion collision. And we usually do this by subdividing it into different stages and approximating them with individual physical models. So in particular, the quark-gluon plasma phase, which is what we're most interested in, can be well described by viscous hydrodynamics. Recently, these hybrid models have been used in Bayesian analyses to constrain the QGP's transport properties. And these are the current estimates for the shear and bulk viscosities. You can see the constraints under temperatures are pretty good, but not perfect. So our goal is to develop better and also more flexible models to get better constraints. So in this talk, we address the current issues with the fluid dynamic and particleization stages. At very early times, the gradients in dissipated flows are so large that viscous hydrodynamics breaks down. So this gap here is usually filled by a conformal pre-hydrodynamic model, but it's not fully compatible with the non-conformal QGP. And then in the particleization stage, the large viscous effects on the emitted spectra may need to be regulated since linear delta F corrections to the hadronic distribution can make it negative. So in my thesis, we developed a far from equilibrium model called anisotropic hydrodynamics, which is primarily designed to handle the rapid longitudinal expansion at very early times. Unlike standard viscous hydrodynamics, we account for the two largest dissipative effects, the pressure anisotropy and bulk viscous pressure non-perturbatively. In a kinetic theory context, these are captured by a leading order anisotropic distribution Fa, and these anisotropy parameters are Landau matched to the longitudinal and transverse pressures, and this allows us to formulate the evolution equations macroscopically so we can repurpose them for the QGP. The advantage of this approach is that we can both model the pre-hydrodynamic and fluid dynamic stages with the QCD equation state, and this ensures a smooth transition to viscous hydrodynamics as the gradients decrease over time. And then for the particleization stage, we derive a new hadronic distribution to capture these large dissipative effects while also staying positive definite, as opposed to the linear delta F corrections typically used in the Cooper-Frye formula. We also develop a particle sampler with several choices for delta F to sample hadrons from fluid cells undergoing a phase transition. And then finally, we combine these two models to help make phenomenological predictions for lead-lead collisions at the LHC. I'm having a hard time with this. Okay, there we go. So first we look at the fluid dynamic stage, which involves the energy momentum tensor of the QGP. And in the usual decomposition, the equilibrium part of T-mu is characterized by an energy density, fluid velocity, and QCD equilibrium pressure, while the bulk pressure and shear stress tensor encode deviations from local equilibrium. In particular, the diagonal component of the shear stress or pressure anisotropy is large at early times, while at later times, the bulk pressure can max out near the quark-hadron phase transition. So in anisotropic hydro, we reorganize them as non-equilibrium components of the longitudinal and transverse pressures. And by using a different set of projections, we arrive at a new decomposition where the largest non-equilibrium effects are encoded in PL and PT, and then you have residual shear components left over. So nothing about T-mu itself has changed since these two projections are equivalent, but we'll see that the hydrodynamic equations involved in these dissipative flows are different. So in standard viscous hydrodynamics, we typically use relaxation equations to evolve the shear stress and bulk pressure, while the conservation laws and QCD equation state cover the equilibrium components. These relaxation equations are partially based off the relativistic Boltzmann equation. And when you assume gradients in dissipative flows are small, the evolution equations are second order. So for example, in the bulk pressure evolution, there are these transport coefficients coupled to gradient forces that take the system off equilibrium. And then the bulk relaxation time term tries to drive pi towards equilibrium. And then you have a similar structure for the shear stress equation. So here the shear and bulk viscosities are modeled with a temperature-dependent parameterization, and these parameters are constrained phenomenologically. And then we compute the remaining transport coefficients, such as the shear and bulk relaxation times, usually with a kinetic model. And in the standard approach, you use light fixed masses, the dashed lines, while more recent quasi-particle approaches use a medium-dependent mass. So between the two, the shear relaxation time doesn't differ that much, but the bulk relaxation time can increase substantially. And then finally, we note that transport coefficients associated with gradient forces effectively receive first-order dissipative corrections. And this is a consequence of expanding the distribution around the equilibrium distribution. But we'll see that the structure changes when we go to anisotropic hydro. So this time we expand the distribution function around Fa, and we expect our the residual delta F correction to have a small effect. And we make this expansion unique by imposing generalized Landau matching conditions here. And this establishes a relation between the anisotropic parameters and the leading terms in T mu nu. And this helps us close the relaxation equation for PL, for example. And you can see that it shares some of the features with second order viscous hydro. You have the same shear and bulk viscosities and the same quasi-particle relaxation times. But then there are these anisotropic transport coefficients coupled to different expansion rates. And we evaluate these coefficients with moments of the anisotropic distribution, which means that these coefficients have a nonlinear dependence on the pressure anisotropy and bulk pressure, as opposed to the linearized relations shown earlier. But this nonlinear relation keeps the viscous pressures in check, even as the gradients are large. So PL more or less stays positive in anisotropic hydro, and similarly for PT. But then at later times, anisotropic hydro transitions to viscous hydrodynamics, because in a limit of small dissipative flows encountered later in the collision, these coefficients can be linearized, and we recover the same structure in second order hydro. To model realistic nuclear collisions, we implement anisotropic hydro in a 3+1D simulation called VAH, which is an upgraded version of the code GPU-VH. It's a flexible package that can run 3 different evolution models, including anisotropic hydrodynamics, viscous hydrodynamics with quasi-particle coefficients, and then the standard approach, which is used in music and many other fluid dynamic codes. The numerical algorithms that we use to solve the evolution equations include the Kirchhoff-Tadmor algorithm combined with the ODE solver. And this is common in other codes. But the new feature in our code is an adaptive step-sized algorithm that automatically adjusts the time step until you hit the CFL bound. And the main advantage of this approach is that we can push back the simulation to very early times, because we're able to resolve the initial expansion rate with a fine time step, and then quickly finish the rest of the simulation with a coarse step. So in the next slide, we compare VAH to VH2, while VH is sort of the middle ground. So here we evolve a 3+1D central lead-lead collision with smooth initial conditions. And for simplicity, we only look at the fireball evolution in the transverse plane. So initially, this energy density cools down rapidly due to strong longitudinal expansion. But then as the longitudinal gradients decrease, the transverse flow takes over and causes the fireball to spread out in the transverse plane. If we look at very early times, you can see the large shear stress from anisotropic expansion makes the PL/PT ratio quite small initially. And if you look at the center of the fireball, there are moderate differences between VAH and VH2, but then as you move towards the fireball edges, the two models differ greatly. So in particular, PL stays positive in VAH while it turns negative in VH2, indicating a breakdown in the latter approach. Generally, negative pressures are a bad sign because they could lead to cavitation, but direction-wise, a negative PL only contracts the fluid in the rapidity direction. So it doesn't have much impact if you're only interested in 2+1D hydrodynamics. So next we look at the evolution of the bulk pressure. And since the bulk relaxation time in VH2 is short, pi quickly approaches this Navier-Stokes solution, and therefore it's very sensitive to the magnitude of zeta over S. But in VAH, the large bulk relaxation time causes a significant delay in the response. So it isn't as strong, and this leads to effects such as increased transverse flow. And finally, we look at the evolution of the residual shear stress components, and relative to the transverse pressure, they're small. So this indicates our expansion around FA is valid for the entire region. Okay, so now we shift gears and talk about the particleization stage, where hadrons are emitted from an isothermal hypersurface that defines the fireball boundary in space-time. And we convert the fluid cells on this hypersurface to particles by computing the Cooper-Frye formula, which generally has a non-equilibrium correction to the local equilibrium distribution. The exact form of this delta F correction is somewhat ambiguous, but people usually make a linear expansion. And the most popular one in our field is the 14-moment method, which has a quadratic momentum dependence. And then these expansion coefficients are linear in the dissipative flows, which allows us to reconstruct T mu exactly. However, this total distribution expansion can have unphysical negative values at high momentum, and this problem becomes severe if the dissipative corrections on the surface are large. So in this particular example, the bulk viscous corrections peak near the switching temperature, so linearized approach would break more often. To circumvent this negative probability issue, we can apply viscous corrections to the Boltzmann factor to keep the distribution positive. This so-called modified equilibrium distribution was first proposed by Pratt and Torrieri, and we improved upon it with our versions called the PTM and PTMA distributions. So starting here, you can see the temperature receives an effective bulk viscous correction, and then you have a matrix transformation that deforms the thermal momentum space P prime. So for example, these shear stress components make the PTM distribution asymmetric in the transverse plane. However, the drawback of this modified approach is that I can't reproduce the energy momentum tensor exactly. In this example, a fluid cell composed of hadrons is subjected to a fixed pressure anisotropy and bulk viscous pressure, while the residual shear stress can vary. And these black lines are the input T mu components that modify the PTM distribution. And then the color dotted lines are the corresponding output when you compute moments of the PTM. And for zero residual shear stress, you can see that the PTM distribution can't reconstruct PL and PT exactly in extreme situations. So we want to build on this, and we can do this by modifying a anisotropic distribution with residual shear corrections. And the resulting PTMA distribution has a more complicated momentum space map, but we can decompose it. So the first two terms belong to the leading order anisotropic distribution. while the residual shear modifications, they break the cylindrical symmetry of Fa. And with this transformation, we can first reconstruct PL and PT precisely after Landau matching them to these anisotropic parameters. And these are the corresponding values. And then as we include the smaller residual shear corrections, we can better reconstruct all the T mu components simultaneously, given by the dashed lines. To highlight the advantages of the PTMA distribution, we compute the continuous Cooper-Frye spectra from this surface shown earlier using either the 14-moment expansion or one of the two modified distributions. Specifically, we plot the PT spectra of pions, kaons, and protons. And relative to the ideal spectra without delta F corrections, there's generally a shoulder enhancement at low PT and a steeper negative slope at high PT. And these softening effects are primarily due to the large bulk viscous corrections. In contrast to the 14-moment spectra, which turn negative after about 1.5 GeV, the PTM spectra stays positive and maintains an exponential-like tail. But the PTM underpredicts the average pressure of each freeze-out cell, and this decreases the mean transverse momentum. But with the PTMA distribution, we can slightly correct for these errors and scale back these softening effects. But for practical applications, we need to sample particles from the Cooper-Frye formula so we can feed them to a hadronic afterburner. And we do this with the IS3D particle sampler that Derek Everett and I developed from the code ISS. It can sample hadrons using 1 of 5 delta F models, including the 3 ones shown in the last slide. If we want to sample particles from the Cooper-Frye, we interpret the integrand as a probability density, and therefore we need to enforce positivity in certain phase space regions with these step functions. In particular, we force the particles to flow out of the fireball, and we also regulate the distribution function f when it turns negative. So even though this regulated Cooper-Frye deviates from the original one, we have no choice but to work with it. So we want to make sure our particle sampler can reproduce these effects. In our sampler test, we use a hybrid surface that has really large bulk viscous corrections. And then we sample a very large ensemble of particles to compute the event average spectra with a high degree of precision. So here the colored histograms are the sampled spectra of pions, kaons, and protons, where the first 2 columns use linear delta F corrections, while the last 2 use modified equilibrium distributions. And we note that this test was done a few years ago, so it doesn't include PTMA, although it's similar to this one. So earlier, we computed the continuous spectra without any delta F regulations, and a similar calculation is shown here. But now that we sample the particles, the linear delta F corrections become strongly regulated once we go above 1.5 GeV. On the other hand, the PTM spectra doesn't require much regulation since it stays positive definite. And we also expect little to no regulation in the PTMA spectra as long as the longitudinal and transverse pressures stay positive. Finally, we compare the sampled spectra to the regulated Cooper-Frye given by the black lines. And when you compare their ratios, you can see the sampler reconstructs it very well with relative error staying below 0.5%. So later, when we use the sampler in practical applications, we're confident that this particle spectra's deviation from the original Cooper-Frye are mostly statistical, since we generate a smaller ensemble of 10 to the 5 particles per hydrodynamic event. So finally, we're ready to integrate the 2 codes, VAH and IS3D, inside the JetScape framework and run event-by-event simulations to predict hadronic observables and lead-lead collisions. So we run about 8,000 collision events and evolve the medium in 2+1 dimensions. Similar to the Jetscape Sims hybrid model, we use the code Trento to generate fluctuating initial conditions for the energy density. And there are several model parameters that control the initial deposition. So first, the normalization factor controls the overall magnitude of the energy density. And then the nucleon width parameter controls the width of the fluctuating hotspots. We'll be adjusting these two parameters later, but for now we keep them fixed. So next we evolved the fluid with 2+1D anisotropic hydrodynamics. And we start at a very early time so we can replace the conformal free streaming in standard viscous hydrodynamic modules used by Sims. But we keep the Bayesian model parameters associated with the shear and bulk viscosities the same. After the fluid dynamic stage, we use IS3D to sample hadrons from the collision. And for now, we just set delta F to the 14 moment approximation. And finally, we use the hadronic afterburner smash, where the sampled hadrons can decay and rescatter until they free stream to the detector. And then we compute the theoretical observables. So here are the preliminary results, where we compute the particle yields and transverse energy, the mean transverse momentum, the anisotropic flow coefficients, and the PT fluctuation measure. Since the Bayesian model parameters have already been optimized for Sims, we reconstruct the best fit to experimental data. But then when we repeat the calculation with the VAH framework with the same parameters, it underpredicts many of the observables. And these large discrepancies are attributed to differences between and VAH and Sims. So in Sims, the conformal free streaming module makes the longitudinal pressure 0 until you switch to viscous hydrodynamics at the switching time, which is about 1.5 Fermi. But in VAH, the pressure anisotropy ratio generally increases over time. So the fireball initially does more work as it expands in the longitudinal direction, and it cools down at a much faster rate. And the smaller fireball generates much fewer particles. Secondly, VAH has a weaker transverse expansion, since its PT is well below the conformal free streaming limit. And this is a consequence of replacing the conformal equation of state with QCD. And as a result, the mean transverse momentum and BN coefficients decrease. But then once you go past the switching time used by Sims, the fluid dynamic stages don't deviate that much from each other, because even though we saw differences in the bulk viscous pressure, the pressure anisotropy more or less starts converging. To obtain better fits to experimental data, we ultimately have to re-optimize the Bayesian model parameters for the VAH framework. But for now, we can just take what we learned to make some quick changes. So here we raise the normalization factor to put more energy into the system to increase the particle yields. And then we decrease the nucleon width parameter to increase the transverse gradients in the initial profile. And this generates a stronger transverse flow for the mean PT and anisotropic flow. So after making these two adjustments in the VAH model, we get a much better agreement with the experimental data. In particular, we're able to reconstruct the VN coefficients and PT fluctuation measure very well. But then there are some observables such as the kaon yield and proton mean PT that might need some work. Finally, we swap out the 14 moment approximation with the PTMA distribution and compare the two. And the results are very similar, except it underpredicts the elliptic flow at high centralities. But these two preliminary calculations are subject to change once we do a full Bayesian analysis. So in this thesis, we developed two software packages to complete an anisotropic fluid dynamic simulation for heavy ion collisions. We showed our hydrodynamic code VAH can evolve the pre-hydrodynamic and fluid dynamic stages with a QCD equation of state, while the ICE 3D model can sample hadrons with a positive definite PTMA distribution. As the first application, we computed the hadronic observables from fluctuating lead-lead collisions at the LHC and reached the same level of predictive power as the SIMS model. In the future, we look to perform a more comprehensive model-to-data analysis by reoptimizing the Bayesian model parameters for BAH. Our software packages also give the community new tools to explore different model combinations. Apart from varying the particleization stage in SIMS, we can also compare anisotropic hydro against different combinations of pre-hydrodynamic and viscous hydrodynamic stages. And then on the theoretical side, we plan to generalize anisotropic hydro to include net baryon density effects. Sorry, I went over time, but thanks for listening.
Great. Thank you so much, Mike. So if there is any question for Mike, we have time for a couple of questions. Yes, and Dirk, please go ahead.
Just a quick technical question, Mike. Very nice talk. You showed a figure of the CFL number that varied as a function of time. Maybe I didn't quite understand what was plotted there. Yes, this one. Why does that vary as a function of time?
So the CFL condition that you're maybe most used to is this one, where it only depends on the lattice spacing. But this is like the ultra relativistic limit. If you assume the maximum speed is near the speed of light, it doesn't depend on the fluid velocity, but generally it does. So this time dependence is the result of the flow that develops in the collision. So initially it's dominated by the longitudinal flow. So it goes like delta eta over u eta, and then these other ones go like delta x over ux and so on. So initially the longitudinal flow dominates, but then as the longitudinal expansion decreases, you have a buildup of transverse flow that overtakes it. So that's just why you have this discontinuity. And then the transverse flow increases and it sort of approaches the ultra relativistic limit here. I don't have an exact line, but it approaches, in this case, it would be delta x over 8. But doesn't quite reach there.
Thank you. Thank you.
Other questions?
Lorenzo, please go ahead.
Yes. Hello, thank you for the interesting talk. I wanted to ask you, could you go to the previous slide, slide 6? Yes, so this profile of the anisotropic distribution one particle distribution function, intuitively, how is it proved that that's the structure? Is it a dynamical attractor of the evolution? Because I've never seen these kind of things. How does one show that that's the structure?
So really it's an on-science, but it's motivated by, I guess, studies that we've seen like in kinetic theory studies. So for example, if you look at the RTA Boltzmann equation, the exact solution when you're in known coordinates, because of the geometric elements are expanding, particularly the longitudinal ones, they scale like 1 over t squared, that you end up having the exact solution is kind of looks like an ellipsoidal distribution. So I refer you to one of Mike Strickland's works where he plots the map of the exact distribution function in momentum space. And it's composed of 2 terms. One of them is a very sharp elliptic-like structure. And then the second term of the exact solution is basically an integration over different ellipsoidal distributions. So it kind of, this on-sense kind of helps capture, one is the free streaming limit when you take these anisotropic parameters to be very small. And then as the gradients decrease over time and approaches the near equilibrium limit where dissipative corrections are small, then this approximately captures the first order terms when you do the linearization. So like if you expand, you can expand FA around F equilibrium, and you get the non-equilibrium effects on the phase space distribution, and they're kind of like ellipsoidal. So it's like a good parametric model that you can use, but it's not like, I wouldn't go as far to say you can prove this. I'm not sure. Maybe you can get something close to it, but maybe not exactly.
Okay, thank you.
Yeah, I know it's kind of a strange looking distribution. So any other questions?
Okay, great. So I think we are out of time. We already have to start the next talk. So there are 2 other questions, but unfortunately, I think we should postpone them to Q&A.
Okay.
Thank you so much, Mark. And let's have a round of